Let's start with the simple part, the equivalent resistance. When we are dealing with resistors, there are two types of connection. The first connection is called the series connection. So when the resistors are in series, it's more like they are in a straight line. Okay, let's call this resistor 1. Let's call this also resistor 2. In series, they can be in multiple numbers. They can also be resistor 3, resistor 4, as long as they are all in a straight line. So how do I get the equivalent resistors of all these two resistors? So because they're in a straight line, what I simply do, the formula for getting an equivalent resistance in series will be equals to R1 plus R2. So if there are 3 resistors, then you're going to add plus R3, depending on how many resistors are in series. So now, let's say, for an example, this was a 4, this is a 2, this is a 1. So wherever there is I1, I'm going to put a 4. Wherever there is R2, I'm going to put a 2. And then wherever there is R3, I'm going to put a 1 ohm. Remember, resistance is in ohms. Don't forget that. So now, my R series will be equals to 4 plus 2, which is 6, plus 1, which is 7, is going to be 7 ohms. Let's go to the second type of connection. The second type of connection is called the parallel connection. How do I see that this is a parallel connection? A parallel connection is always identified by a junction. So these two resistors are separated by a junction in between them. And then they'll be rejoined again. Let's call this one my R1. Let me call this my R2. Right? So when you see something like this, you must know that these resistors are what? Are in parallel. Right? How do I get the equivalent resistance of the parallel circuit? So it's going to be 1 all over R parallel, which is equals to 1 all over R1 plus 1 all over R2. So since we have all this, we can simply rewrite the same formula without putting a 1 all over so that we don't make mistakes. We just write R parallel equals to 1 all over R1 plus 1 all over R2, and then we put a negative 1. So if you didn't put a negative 1, you can simply do this. But remember that after you do your answer in the final day, after you've substituted the value, you must make sure that you turn your answer to be upside down and make sure that it's simplified. Remember, there is a connection between a parallel series resistor. What am I saying? What I'm saying is, let's say there is a resistor 1 here, and there is a resistor 2 here, and there is another resistor here, resistor 3 here. Do not make a mistake when you see these resistors. The first thing that you need to do there, because these resistors are in a straight line, do you see that, right? So which means these resistors are in series. So you must first add these two resistors. After adding these two resistors, the sum of these resistors will be a parallel connection of these resistors here. And then that's how we're going to do, which means in other words, it's going to be R series equals to R1 plus R2. And then when you get the sum of these resistors, what you're going to do, you got your R series. So now your R series is now in parallel with R3, which means in other words, my R parallel will be equals to 1 all over R series plus 1 all over R3, which is this one. And then you put your negative 1 there. And then you get your parallel circuit. Okay, here we're going to focus on how to get the equivalent capacitance. Remember, now, we all know a capacitor is a component that looks similar to this thing. So now, what I explained on resistors is in opposite of what is happening on capacitors. So let's say my capacitors are connected in series. Let me call this C1 and let me call this C2 for capacitor 1 and for capacitor 2. So when the capacitors are connected in series, for me to get the equivalent capacitance, I'm going to say C series equals to, then it's going to be, I open my bracket, 1 all over C1 plus 1 all over C2, and then I'm going to put a negative 1. and this is going to give me the equivalent capacitance of the capacitor that are in series. If there are 3, I'm going to simply add the third one. Let's say there is a third capacitor here. Let me call it C3. So it's going to be the same thing, 1 all over C3. And then don't forget to put that -1 because it's an inverse of what's really going on. So these are the equivalent capacitors in series. Let's go to the equivalent capacitors that are connected in parallel. So this is junction. Let's call that capacitor 1. And let's come on this side and we call this one the capacitor 2. So since they are connected in parallel, I told you that what is happening on resistors is an opposite of what is happening on the capacitors. So if this is C1 and C2, which means when they are in parallel, you treat them as if they are in series. So my C parallel, the equivalent resistors that are in a parallel circuit, will be C1 plus C2. You treat them as if they are in series if you see them in parallel. And that's how it happens. So remember that on capacitors, they can try, what do you call this? On capacitor, they always give you this, I call it the moon method. If you see microfarad, you know that, okay, let's say -3, -6, and -9. If you see M, that's micro. U, that's -6 times 10 to the power -6. And then -9, that's what? That's a nano. So you always have to remember that. So you know capacitors in most cases, they're given this, which is the U, which means you always remember if it is given to you a certain number, they say 6 microfarad, which means you need to know that it is 6 times 10 to the power -6. Right, now we are going to focus on how to calculate the time constant if we're given an RC circuit. What do I mean by RC circuit? R and C, that's a resistor and capacitor connection. So if you see a resistor and the capacitor connected, that circuit is called an RC circuit. So now, you know that the formula for time constant is equals to, time constant will be equals to R equivalent, the equivalent resistance of the resistors, multiplied by C equivalent, the equivalent capacitance of the capacitors. Now, we have to get the R equivalent, which is the equivalent resistance of the circuit that is in here. So now, these resistors are in series, right? And remember the formula for the R series equals to R1 plus R2. So what is R1? My R1 is 500 plus R2. What is my R2? It's also 500. So if I add these two, they're going to give me what? 1,000. So it's going to be 500 plus 500. Then, which means my R series there will be equals to what? Will be equals to 1,000. So in other words, I come here, for me to calculate my time constant, I already have the R equivalent, which is equals to 1,000 ohms, multiplied by. Now I come here on the capacitance. Remember, the capacitance that are in parallel, I treat them as if they are what? They are in series. So it's an opposite of what is happening here. So in other words, which means my C equivalent will be equals to C1. Let me name this as C1. Make it a little bit bigger, C1. And the other one is my C2. So now C1 and C2, because here they are in parallel, the equivalent resistance of a parallel circuit, it will be 20 plus 60, because I treat them as if they are in series, opposite of what is happening on the resistors. So which means, in other words, 60 plus 20 is going to give me what? 80 microfarad. 80 UF. So now that I have the total equivalent of the what? Of the parallel circuit, I'm going to come here now. I'm going to say 80. Remember, I've already told you that the UC is the same as times 10 to the power -6. Do not forget that. So it's the same as times 10 to the power -6. So when we multiply this, our time constant will be equals to here 0.08 seconds. Right, we are going to deal with question 1.4 on the tutorial guide so that we can simplify what's really going on there. So now guys, there's one thing you need to understand about the capacitor. When the capacitor is fully charged, it will operate as an open circuit. especially on the DC. Which means, in other words, when let's say the capacitor is charging, and when the capacitor fully charged, what will happen is that it will be like an open circuit, which means it will cut current from going on the other side. So this is what we're going to explain on the question that is being asked on A, 1.4a. So which means, in other words, they say what will be the current after the switch has been closed for a very long time, which means the capacitor is now full. In other words, when the capacitor is full, I've already explained that under the DC circuit, the direct current, the capacitor will operate as an open circuit, which means the current that will be on the resistor will be zero. If the circuit opens up here, it means it doesn't allow current to flow through. So the current that will be found on this one will be equals to zero. That's the first point that we're going to explain. So that's why you see that they said it's going to be 0 amperes. And then we're done with the first one. So now let's focus on the second now and simplify the concept of what's really going on. Right. They say an AC circuit resistor or an AC circuit of a resistor, right? RC circuit, which means it's a resistor, capacitor circuit, right? With a resistor of 1 kilo ohm, they've already given us the size of the resistor. And the battery of 120 volts, they gave us the size of the battery. And the two capacitors, they gave us that they're connected in parallel, which is 20. And then there is a 60 also, C1 and C2. They're given to us. And they're connected respectively. Initially, the capacitor is uncharged. They're telling you that initially the capacitor is uncharged, which means the switch is open. And then they say the switch is closed at T0. That T0 seconds simply means it is closed immediately, right? So now, which means it's now beginning to charge now. It wasn't charging at all, so it is beginning to charge now. So which means our switch is now closed. Let's see what happens. So when the switch is closed, the capacitor begins what? Begins charging. As long as the capacitor is not yet fully charged, current will still flowing on the other side. It's only when the capacitor is fully charged where it will now operate as an open circuit, where now the current will be cut from flowing to the other side and stuff. So let's look at number one. On B, we've already explained the first part. B says, what is the time constant of the circuit? We already know that time constant is equals to R equivalent. Remember that? R equivalent, let me make it a little bit bigger. R equivalent multiplied by C equivalent, which is the formula. Time constant is equals to R times C. So do I have the R? Yes, it's 1 kilo ohm, which is the same as 1000, right? So when we multiply this, it's going to give us 1000, which is 1 kilo ohm, right? Or 1 times 10 to the power 3, multiplied by the equivalent capacitance. Remember, let's come to the capacitors. When the capacitors are connected in parallel, we treat them as if they are in series, which means, in other words, we are going to add these two capacitors. For me to get the equivalent capacitance, I'm going to say R parallel is equals to, C parallel, is equals to 20 microfarad plus, let me add it here, down here for space, 60 microfarad. So the total of these is going to be 80. So remember, I told you that this one simply means times 10 to the power what? To the power negative 6. So it's going to be 80 multiplied by 10 to the power negative 6. When I multiply this, I'm going to get my time constant to be 0.08 seconds. And this is the answer that they get on the guide. Now, the next question there said, how much charge will be stored in each capacitor after a long time has elapsed? Remember, we are calculating for the charge in each capacitor. Remember, the formula for charge is equals to C is equals to Q over V. So if you are looking for charge, we can simply manipulate the formula there. Then my Q will be equals to C times V. I cross multiply, it's more like there is over 1, then this is what I get. So now, I'm going to look for the charge in the first capacitor, right? And then I'm going to look for charge in the other one also. And I'm going to simplify. The V is already given, which is the one that is supplying there. Remember that? And then it's going to be Q equals to. Remember that when we come in the parallel circuit, the voltage will be divided equally. So 120 will go up there, 120 will go down there. Very important for you to know that. So which means the voltage is divided equally. It's only the current that is divided unequal. Then when we come here, what are we going to see? We are going to see C multiplied. What is the C there? C micro, which is the same as times 10 to the power negative 6 multiplied by the voltage, which is 120. Then I'm going to get that the first capacitance, when I multiply it, is going to be 2.4 millicoulombs. Charge is measured in coulombs. Let's go to the second one. So let's say this is Q1, charge 1 for the first C1. So the second one, still going to be the same thing, just that this time there is a 60 times 10 to the power negative 6, which is this, multiplied by the voltage there, which is 120. When you multiply it there, then the charge is going to be equals to what? Is going to be 7.2 millicoulomb. And that's how we get the second question. All right. What you need to understand is that there is a formula for when a capacitor is charging and also a formula when a capacitor is discharging. We need to know the difference between the two. So now when a capacitor is charging, right, is when current is actually flowing right from the battery and going right down to the what? To the capacitor. But if current is cut off there, right, there is a possibility that the capacitor will start discharging. So let's look at that. So the first formula for charging, Q initial, is the initial charge that is there multiplied by 1 minus e to the power of negative t all over RC. This RC is the same as the time constant, right? You can say time all over time constant, right? So now, what you need to understand there is, you are going to put the initial charge that you have, the initial charge of a charge, probably maybe we calculated the two charges previously, and then you're going to put that initial charge there. If only, you only use this formula if the capacitor is charging. But if the capacitor is discharging, let's simplify this. When the capacitor is discharging, you simply get rid of the negative one. That's all. So it's going to be Q equals to Q0, and then you get rid of the negative one, e to the power all over RC. And then you close. No need for us to put the brackets there. And then this is how it is. So now, so this is the charging and the discharging, right? But here, we are talking about the charges and stuff. So let's simplify it now. So now that you have seen the two formulas and how they operate, now let's explain what is happening on time constant. Okay, there are times where they would say it is charging at 2 times constant. It is charging at 3 times constant. It is charging at 4 times constant. What is happening there? If you hear 2 times constant, 3 times constant, 4 times constant, this is what they mean. When they say 1 time constant, they've actually given you time. So time is equal to 1 times constant. If they say 2 time constant, wherever there is time, you are going to simply say T equals to what? 2RC. In other words, let's go to the formula now. Still remember the formula? Q equals to Q0. And then I'm going to say open bracket 1 minus. And then when I come to this part here, still remember it's going to be E minus T all over what? All over RC. When they say 1 time constant, which means wherever there is time, I'm going to put what? At 1 RC. So it's going to be 1 RC. In other words, this RC and this RC will cancel off. So my formula will be manipulated to become 1 minus e to the power of negative 1. And this is the one. If they say 2 time constant, so wherever there is wherever there's 1, I'm going to substitute by 2. So the same thing will be repeated, just that the difference here now there's going to be a 2. And then which means when it is 2 time constant, it's going to be a 2 here. 3 times constant, same thing. 4 times constant, you put 4. 5 times constant, you put 5. And then you will get this as the final product of the first part. Right, we have already explained about the 2 times constant, right? In the question D, they said when the capacitor is 2 times constant, which means in other words, they've given us time. So we are going to find our initial charge, which is the 2 ones that we have already calculated previously. Why am I using this formula? Because here the capacitor is charging, right? The switch is closed. So in other words, we are going to put negative 2. Remember, the negative 2 is for 2 times constant, because the question says 2 times constant. What is the initial charge for the first capacitor? It's 2,4 microcoulomb, the one we calculated previously. And you just say 1 minus e to the power of 2 time constant, and then the charge that you're going to get there is going to be 2.1 microcoulomb. That's for the first answer. For the second one, you're going to do the same again. We do have the initial charge. The initial charge that we calculated was 7.2 microcoulomb, right? Since it is 2 times constant, we're simply going to say 1 minus to the power of negative 2, we close bracket, and the answer that we're going to get here is going to be 6.2 millicoulomb. Then you're done.